Okay, let's just dive right into this. Welcome to the Explainer. Today we're taking a seriously fascinating journey to demystify the foundational concepts of electrical bond graphs. If you've ever stared at the complex pathways of an electrical circuit and just wondered, how do engineers actually make sense of all that invisible energy zooming around? Well, you are absolutely in the right place. We're going to break down these concepts, and don't worry, not with dry, complicated math, but through a highly visual adventure that's kind of going to change the way you look at energy.
But hey, before we get completely lost in the technical weeds, I want you to consider the question right in front of you. Imagine you've got a bright light bulb just sitting there in front of you. To make it even brighter, do you need to increase the effort or do you need to increase the flow? Just keep that mental loop open. Ponder it for a second, right? Because we are definitely going to solve this exact interactive challenge by the end of our explainer today.
All right, let's kick things off. Enter the circuit board, a microscopic journey.
So in the source material we're exploring today, we actually follow a fictional protagonist named Commander Energy. Just imagine stepping right alongside them, shrinking way down, and literally walking inside a giant circuit board. Our core mission here isn't just to gawk at the invisible forces, though that's pretty cool, but to figure out how to map these real-world electrical properties into a standardized graphical language. And actually, that is exactly what an electrical bond graph does. It translates the messy physical world into this universal visual language for engineers.
Moving right along, voltage, the push of effort.
Okay, let's start with the formal scientific definition. We all know voltage is the initial pressure required to move energy through a circuit. Basically, without it, the whole system just remains completely dormant. It's that all-important starting push that forces everything off the line.
Now, let's look at this comparison. On one side, we have our standard scientific definition, right? But on the other, we have Commander Energy's physical experience of it while inside the board, identifying this voltage simply as the pressure coming straight from the battery. And here's the key. In the logic of bond graphs, this pressure acts as the effort variable. So whenever you think of voltage in this framework, just think of the battery's pressure and categorize it strictly as effort. It's essentially the spark that gets the whole shebang going.
Next up, current, the stream of flow.
So moving from pressure to actual motion, current is the literal physical movement of electrons through the circuit. If voltage is the pressure pushing things, well, current is the active, moving stuff within the system itself. And as you'll see, Commander Energy witnesses this movement and identifies it as a literal stream of electrons just zipping past. Because of this perfect physical mimicry, bond graphs categorize current as the flow variable. It's the steady stream of energy successfully navigating the pathways of the board.
All right, let's put it together. Decoding the bond graph.
I want you to treat this translation chart kind of like a decoder ring or a map of an ancient tomb. It shows exactly how standard electrical domain symbols map directly to their specific bond graph nicknames. Check out the left side, voltage and current. Now look on the right, their bond graph equivalents. Voltage maps to effort, which is represented by a lowercase e. Current maps to flow, represented by a lowercase f. So whenever you see an e or an f in a diagram, boom, you immediately know you're looking at the effort of voltage and the flow of current. It's a real game changer.
As our source material beautifully states, this entire narrative is, quote, a conceptual guide for translating physical electrical properties into a standardized graphical language. And you guys, this mapping is absolutely crucial. It completely unlocks the ability to read and design incredibly complex systems without getting lost in the invisible physics.
Okay, moment of truth. The light bulb challenge.
Let's jump all the way back to that interactive challenge I posed to you at the very beginning of this explainer. Remember? You have a bright light bulb. To make it brighter, should you increase the effort, which we now know as voltage, or the flow, which we now know as current? So what do you think? Have you figured it out?
Let's just walk through the logical steps to answer this challenge together. Step 1, we successfully identify that effort is voltage, so that's the pressure. Step 2, we identify that flow is current, that's the stream of electrons. And step 3, well, this is the secret. You realize that to understand the total energy, the true brightness of that bulb, both are needed. No way around it. You absolutely need the push of the effort to move the stream of the flow. They are intimately, completely connected in the logic of the circuit. Increasing the total energy transferred requires understanding exactly how both that pressure and that movement interact with each other.
Okay, let's distill Commander Energy's entire microscopic adventure down to these core takeaways for maximum retention. First up, remember the battery pressure. Voltage is the effort variable, represented by E. Second, remember the stream of electrons. Current is the flow variable, represented by F. And finally, the overarching purpose here. Bond graphs exist to elegantly map these complex physical properties into a clean, standard graphical language. Simple, right?
So, believe it or not, the electrical domain is really just the beginning here. I want to leave you with this final thought to ponder. If the simple logic of bond graphs can so perfectly decode and translate the invisible forces of electrical circuits into a visual language, what other complex physical domains of energy, like mechanical, hydraulic, or maybe even thermal systems, could this standardized graphical language simplify next? The universe of energy is incredibly vast, and you know what? You now have the translation key to start exploring it. Thanks for joining me on this explainer, and definitely keep learning.